everyone, welcome to our second lecture for week 1. Today you are going to need a couple of things to gather together before you start viewing the lecture. You'll need your periodic table, the one that I mailed to you. You'll need your calculator just to do some basic math functions. You'll need your pink sheet, homework number 2, and the chemical connections rubric. If you haven't yet taken a look at the chemical connections rubric on Joule, please do so right away, pause it, and then come right back, because I'm going to spend a little bit of time talking about that and explaining what I'm expecting of you for that particular assessment. Okay, so the chemical connections activity is basically just a way for you to use your nursing experience and to tie that into the concepts we're learning in chemistry. You'll notice that in the book, if you go to the very front of the book in the index, or in the table of contents, you'll notice that there are these little blurbs called chemical connections in each of the chapters. And basically what I want you to do is just page through a couple of those chapters that we'll be talking about in class. It can be something that we're talking about this week or something that we're not even talking about until week 7 or 8. It doesn't matter to me as long as it's a topic that we're covering in this class. So find 2 of these topics that interest you personally. One of the examples that I looked at was one about hypothermia and hyperthermia in, I think, the first chapter of the book. If that's something that interests you, if you've treated a patient with that sort of condition, or if it's just something that interests you personally, you can select that as a topic. So you need to just pick 2 of those topics, and what I'm expecting of you for this week is to just post what your 2 topics are in that forum where it says Chemical Connections Selections forum on Joule in week 1. So all you have to do for that is to make sure that you just tell everyone what you're picking. If somebody else picks your topic, you have to find something else. We can't have 2 people doing the same topic because we want to try to get a breadth of topics that are covered. So please post your responses on there, and as long as you do that before next Tuesday, that's fine with me. After I have everybody's topic selections, I will go through and give you assignment deadlines for each of your topics. You won't ever have to do 2 in 1 week, and everyone will be doing them sort of spread out throughout the class. So you don't have to worry about, if you pick 2 from the same, and I think that on the rubric it says that you can't pick 2 from the same chapter. So go back and read that rubric and make sure that you're following all the rules and everything for those topics. If you have any questions, just send me an email. Okay, then let us get started with today's material. Today we're going to be spending some time with atomic theory. Oh, and after my debacle of uploading videos on Tuesday, I am going to only be taping 20-minute sessions at a time so that it doesn't take 2 hours and 45 minutes for the videos to upload. So if you hear a little beeping or blurping, it's my alarm to tell me to start a new movie. Okay, so back to atomic theory. Atomic theory is the basis for all of chemistry. We're talking about how atoms are structured so that we can learn about why chemical reactions take place. So just a very basic overview of atomic theory. The smallest parts of matter that can be differentiated between the elements are called atoms. There are 3 parts to all atoms. The first part, well, there are 2 parts to atoms, and there are 3 particles in atoms. The first part is the nucleus, and inside the nucleus we have things called protons and things called neutrons. Each proton has a charge of +1, and so we sometimes abbreviate protons as small p with a plus in the superscript. Neutrons have no charge, so they're abbreviated small n with a 0. They are also located in the nucleus. The number of protons is what makes each element different from the next. So in order to differentiate between an element of gold and an element of copper, there are two different numbers of protons. The number of neutrons varies, but that's not important to an atom's identity. And the second part of the atom is what's called the electron cloud. In the electron cloud is only one kind of particle, that's the electron. Each electron has a 1 minus charge, and so we abbreviate electrons E minus. This is something that you'll want to make particular note of because I will from now on abbreviate the word electron as E minus. So just take note of that. Electrons are what participate in bonding. So while the protons are what give an atom its identity, electrons and their behavior is what determines how those elements are going to react with other elements. Okay, so this is what an atom actually looks like. You have the nucleus here, and inside the nucleus are protons and neutrons, and the number of each is dependent on each individual atom of every element. The nucleus is very small, but it accounts for it's small in size. There seems to be a lag in my smartboard today. So the nucleus is small in actual size, but it is large in mass. So even though it's the smallest physical part of your atom, it's the place where almost all of the mass of your atom is concentrated. So we have protons and neutrons. And then outside the nucleus is the electron cloud. And there are electrons inside that electron cloud. The electron cloud is really, really big. But it has almost no mass. One of the assumptions that's made in atomic theory when we are going to practice it is that we're assuming that electrons have actually no mass. While electrons do have a mass, it is so much smaller than protons and neutrons that it's almost negligible. Okay, so this is how the atom is structured. To get a good perspective of this actual size of a nucleus and an electron cloud, imagine Lambeau Field. Now I'm talking about this, the field itself, you know, where they play, all of the stands and all of the parking lots around the stands. If you took a pencil and you held it at the middle of the 50-yard line, the top of your eraser would be like the size of an atom's nucleus. And the perimeter of the stadium around the parking lot, that would be like the size of an electron cloud. So you're almost comparing apples and oranges when you're talking about the size of a nucleus versus the size of an electron cloud. But the curious thing about it is that all of your mass is concentrated in that eraser tip basically, and all of the outside, out to the parking lot of Lambeau Field, and you know that's a pretty good size, is all where the electrons hang out. The reason the electron cloud needs to be so large is because you have all these particles of the same charge. And now you know from your own experience that opposites attract and like charges repel. So if you have all of the same kind of charge in your electron cloud, all of those electrons are going to want to be as far from each other as possible. That's the reason why your nucleus is tiny and your electron cloud is huge. Now you might be thinking, well, but Michelle, what about the nucleus? There are only plus charges in there. The neutrons are charged, so isn't that the same thing? Why is that so compact? Well, the difference between the nucleus and why it is so compact is because you have those neutral charges that are sort of spreading out that charge concentration. So the protons can be closer together because there are those spacers, the neutrons, in the nucleus of the atom. Okay, get your periodic tables out. Well, let's talk about some elemental symbols. You'll notice on your periodic table that you have all of these black letters. Some of them are red. Those are the elemental symbols for each of the elements. Now, in my regular general chemistry class, I make my students memorize all of these elements and their abbreviations and how you spell their names and all of that. I'm not going to make you guys do that because for the small, short amount of time that we're together, that's not necessary. So consider yourself lucky. But as you can see, those abbreviated symbols are abbreviations for longer words. So for example, if you can find element number 6, that's carbon. Carbon's elemental symbol is C, and its element name is carbon. So we can put things around this carbon to identify what each individual atom looks like at any given time in a carbon atom. Okay. So I'm just going to use a generic elemental symbol, X. There is no element that has the abbreviation X. So X is just going to be your symbol from the periodic table. And then you can place a number in the upper left corner. That's abbreviated A. That's what's known as your mass number. Mass number is calculated by adding the number of protons plus the number of neutrons. Protons plus neutrons. The reason that's called the mass number is because remember I said that almost all of your mass is in the nucleus of your atom. So by just adding together the number of protons and neutrons, that's what we're getting for our mass. Protons and neutrons have about the same mass. It's not exactly the same, but we're going to consider that it is the same. And we consider that one proton has a mass of 1. Same for neutrons. Okay, so then down here on the bottom left, you can place a number, and that number is referred to as the atomic number. The atomic number is calculated by the number of protons the atom has. Remember I said that every atom has a unique number of protons? So just by identifying how many protons you have, you can identify your element. If I asked you to find the element on your periodic table that has 4 protons, all you'd have to do is look at the upper left corner of your periodic table. Those big numbers are the number of protons that each atom has. So element number 4, the element that has 4 protons is beryllium, Be. Okay. And then in your elemental symbol, you can place a number also in the top right corner, and that is what we call our charge. Charge is calculated by taking the number of protons minus the number of electrons in our atom. Now, this is something that's very important to have a little side note about. Electrons are negative. So if you have one extra electron, have a -1 charge. Adding electrons lowers the numerical value of your charge. If you have one less electron, you have a +1 charge because there's an abundance of protons versus electrons. We'll be talking about this more in depth in a little bit. Okay, let's talk a little bit about isotopes. Isotopes are atoms of the same element which means that they have the same number of protons but they have different number of neutrons. An example of this are the three forms that carbon can take in nature. There's carbon-12, the most prevalent, carbon-13, and carbon-14. Carbon-12 has an atomic symbol that looks like this. It has a 12 up here, that's the mass number, number of protons plus number of neutrons, and a 6 in the bottom. That's your atomic number. If you have carbon, your atomic number better always be 6, because that number can't change. If it's a different number, you have a different element. Carbon-13 looks like this. 1 extra neutron. And carbon-14 looks like this, 2 extra neutrons. Now, each of these three types of carbon occur naturally in the environment. And carbon-14 is the radioactive type of carbon. It's what's used to date really old stuff. So determining how much carbon-14 a substance has and calculating its half-life is how you can date old things like artifacts. Now, if you take a look at your periodic table, you'll notice that there is, right next to the very large blue number at the top, there's a smaller red number. That's your mass number. And so for carbon, on the periodic table, it says that carbon has a mass number of 12.0107. Okay, so you're probably thinking, but how, you said that each proton and each neutron has a mass of 1. How do you get these decimal points? Well, the thing is that each of these three substances occur naturally in nature, and they occur to a certain percentage of all of the carbon that's in the universe. And so this mass number on your periodic table is calculated based on a weighted average of each of the isotope forms of your substance. It's calculated exactly the same way that you calculate grade point average. An A in a 5 credit course is going to weight more heavily than an A in a 1 credit course. And that's exactly the same way this is calculated. I don't know what these numbers are exactly off the top of my head, but I think that carbon-12 accounts for 98% of the carbon in the universe. I think carbon-13 is something like 1.7%, and I think that carbon-14 is something like 0.3%. So obviously, the amount of carbon-14 isn't going to increase the mass number of carbon tremendously because it only accounts for 0.3% of all the carbon in the universe. That is my alarm. So we'll stop and continue with part 2 in a moment.